Hi, welcome to the Microsoft Research Summit 2021. I'm John Langford from Microsoft Research, and I'm going to talk about key research challenges for real-world reinforcement learning in the coming decade. All right, so let's start with what reinforcement learning is, just so we're all on the same page. Reinforcement learning is a situation where you have an agent that's interacting with the world. The world sends some observation to the agent. The agent then has a policy. It uses the policy to choose some action, and that action is then acted upon the world. The world then sends back maybe another observation. The agent then uses its policy to choose again what to do, and then maybe there's some reward that is sent to the agent when the agent does something good. So the goal in reinforcement learning is to maximize the rewards. You want to figure out how to choose the actions so that you can achieve the greatest reward possible. So this is the kind of platonic version of reinforcement learning. And it turns out there's quite a bit of interesting details in how this gets implemented in the real world. Okay, so machine learning and reinforcement learning in general have been say conflated. With AI, reinforcement learning has become the way that people hope to achieve AI in the real world. And I think it's interesting to take a look at how this compares to natural intelligence. So at the basic kind of worm level, we know that worms can learn to seek and avoid things based upon reinforcement feedback. But if you go beyond that, it starts to become substantially more difficult. If you think about a hunting spiders crawl around on the ground. They plan out their path. They have eyes so they can see, so they get a very rich sensory information. Once you start asking, can we do this, it starts to become challenging. It becomes much more of a research question. And then you can go beyond that. You can say, oh, what about a wolf, right? So a wolf is doesn't just have vision, it doesn't just have rich sensors. It also has other wolves that it works with. So there's cooperation. And then wolves also have a memory. They remember things from the past, and they can act based upon their memories of the past. Then you can go beyond that. This is my daughter. And my daughter, in terms of the log loss of her English, is actually a work in progress. But I have to say there's something there in the sense that you can talk to her. She has ideas, she has thoughts, she can try to communicate them to you. And when you manage to overcome difficulties in language, you actually understand what she says. There's a fundamental abstraction, ability to abstract, and ability to communicate an internal state, which is lacking from many of the systems that we have right now. So trying to judge this from the viewpoint of where we're at in developing intelligence, where we're really at right now is all of these advanced things, the rich sensors, the planning, the cooperation, the large memory, the communication, the abstraction, all of these are situations where research projects exist to try to address these, but they're not well-solved problems. They're not kind of routinely, oh yeah, we know how to do that kind of problems. They're like PhDs get applied in order to demonstrate some capability along these lines kind of problems. On the seek and avoid, though, we actually have products. We have a product that exists now. So one of these is the Personalizer service, and this is something that I'm helped work on creating. There's a product team now at Microsoft that enables you to personalize web pages, and of course you can actually do much more general things because you feed it features. It tells you which action to take, and then you tell it the reward, and it just kind of learns automatically how to do better and better over time. So the gap here between having a product that we can use routinely and a research project is what I'm trying to emphasize. We would like to do research so that we can achieve a point of use where a point of usability where people can just routinely use things. And now the question for this talk is, what are we going to see? What research areas right now are going to become products in the next decade? All right, so we have a product for kind of simple seek and avoid style reinforcement learning. We can go beyond that, and the question is, what happens in the next decade? Where will we see new kinds of computerized intelligence, artificial intelligence, getting deployed and used in a routine fashion, just like we can use the Personalizer service right now? And there's sort of two areas that where I believe that in the next decade we will come to see routine usage. One of these is contextual resource allocation, and the other one is learning to interpret people. I'm going to talk about contextual resource allocation first, just to give you a sense of things, and then I'll go on to learning to interpret people. Okay, so what do I mean by contextual resource allocation? So there's a lot of tasks where you're making some decision about how you're going to use a resource, and you would like to do that based upon context. So an example of this might be the heating, ventilation, and air conditioning for the occupants of a house. You can imagine that future houses have the property that every room has its own independent HVAC effectively. It's all through some sort of shared system, but the system can control how much cooling goes to an individual room. And it can do this based upon the preferences of individual people in these individual rooms. Okay, so that seems straightforward, but now you have things like context, like maybe there's some weather outside. Maybe the house gets damaged in some way. Maybe a window is left open. All of these sort of change the equation as far as the dynamics of heating and cooling the house. And you would like a system that just sort of automatically learns to optimize these things based upon whatever context there is and whatever history it observes. So it seems like something where we're starting to see advances in these directions, and in order to really get there, we're going to want to be using reinforcement learning. Another one is a cloud. So you have these enormous data centers where people run virtual machines, and now there's a question about how these virtual machines get allocated on the cloud. In order to do this well, you need to take into account many different constraints. There are finite resources. There's a lot of internal state that must be taken into account. There's also like the time of day. There's various demand signals. There's a lot of context which could be used effectively in order to do this as efficiently as possible. Another example is inventory management at stores. So at stores, they sell things on shelves. They would like to essentially order things so that they arrive just as the thing is sold, so that there's always something on the shelves and they never have too much and they never have too little. Doing that effectively requires using context a great deal. All of these kind of contextual resource allocation problems are amenable to reinforcement learning. Traditionally, they've been solved by optimization approaches. And in optimization approaches, I think that the classical ones, at least, tended to not take into account context very effectively. So all the different observations about the weather or how many people have bought a particular thing in the past, all of these details get shifted into like a forecasting system. And it turns out that often you want to actually learn to choose what to do, not merely try to predict what will happen. Because if you can learn to choose what to do, you can more effectively take into account well, essentially, when you're doing forecasting approaches, you're going to have kind of a two-level error approach, right? Because you could have an error in your forecasting, and then you could have an error in what you're going to deduce to do based upon the forecast. If you're learning directly how to do automated inventory management or how to do HVAC for the occupants of a house, you eliminate this sort of double error approach, which allows you to potentially achieve much better performance. And this can matter a great deal, right? So if you go and you look at where global warming is difficult, it's often difficult for houses because houses are reliant upon natural gas, for example, to heat things up. And shifting away from natural gas is tricky. If we can figure out how to optimize the way houses work so that they're 5% better, that makes it has a huge impact on global warming in general. Okay, so this is contextual resource allocation, and now the question is, how does this work? So there are existing approaches people have taken to try to solve these problems. And the existing approach essentially takes a model of the world, and then you have an observation which feeds into your policy. The policy chooses some action, and then that acts in the model, and then you have another observation, and then the policy chooses an action, and then eventually you get a reward. Okay, so this approach can work, but if you go and you look at what happens in practice when you try to use this approach, it ends up being somewhat challenging. And now the key question is, why is it challenging? What goes wrong? And what goes wrong is actually hiding in plain sight. It is the model, right? So if you want to succeed with this kind of approach, you need to have a good model. If you want to have a good model, you need to have somebody who's pretty expert at in the domain create the model. And even then, sometimes it doesn't work, right? Because there are some things that experts wouldn't know how to model. I think that heating, ventilation, AC type problems are ones where an expert could try to create a model, but something like an open window could defeat the model pretty effectively. And then what do you do when that happens? Well, what happens is, in that situation, is you get something which appears to work well in practice in your model, but when you go and you deploy it in the real world, you discover that it doesn't work. That there's something which is not adaptive enough or not well suited to the actual application. So this is the first kind of key observation. If we want to routinely apply these techniques, these contextual resource allocation approaches, we need to avoid programming a model and instead learn the model. So to succeed reliably, we're going to have to learn the dynamics of the world. And now the key question is, how do we do that? This is an enormous change from where we are in reinforcement learning, because where we are in reinforcement learning is much more in the seek and avoid. There's many approaches for trying to improve on an existing policy by considering small deviations from that policy and improving on that. But maybe we need to go beyond that. We need to instead think about how do our actions affect the future world, and then based upon that, we can start trying to plan within these dynamics in order to create a policy which will achieve good performance. And then if the dynamics in the world change because somebody opens a window somewhere, well, then you can easily plan to cope with that change because you know the dynamics of the world and you don't have to kind of relearn everything about how to achieve a good HVAC system. So 10 years from now, in a decade, I believe that we will conquer this problem. I believe that we will be able to routinely learn the dynamics of the world and cope with changes in the dynamics of the world rapidly so as to achieve good performance in an adaptive fashion, allowing us to address all these problems that I mentioned earlier. Right? So the house that optimizes the HVAC, the cloud, maybe you add some machines or maybe some machines fall apart, but you can just optimize. You have a dynamics to the implied world associated with these things. And now because you have that model of the world and because you can modify that model of the world on the fly as the real world changes, you can adjust and plan and execute effectively so as to solve these problems. This will make an enormous difference. Making the world work better by 5% is incredibly valuable to the world in many ways. Okay, so that's one thing. In a decade, we will conquer contextual resource allocation, and it will make an enormous difference in what happens. In a decade, I think we'll also learn how to interpret people, and it will make an enormous difference in what we see. So let's just think about learning to interpret people a little bit. So you have a person who sends some observation to your computer agent. The agent has a policy. It is going to choose some action based upon that policy, and then there's a reaction that comes from the user. So instead of having a reward now, we have a reaction. So that's something which is more complex than a reward. It's a set of observations about what the user does next. How do we actually learn here? So let's take a look at what this might mean. Suppose that you have a Windows laptop and they show you a pretty picture for a login screen. On this pretty picture, you can like what you see, or you can say, oh, I dislike it, or you can click on things, or you can just ignore it and log in. For each of these actions, how good is that action? If you want to try to choose what the login screen should be based upon the user's reaction to things, should you be trying to optimize for clicks, for likes? How much better is a like than a click? A dislike is obviously bad, but is it worse? Is it much worse than an ignore? Or is it ignore very similar to a click? Is an ignore like a like? All of these are questions you could naturally have. And figuring out what that right reward function is actually kind of tricky because it's not obvious what it should be. There's no formalism in standard reinforcement learning for learning the reward function. Instead, what you do is you learn given the reward function. So I think the key question is, how can we effectively learn the right reward function to interpret this reaction from a user? Right? So it turns out there is a way to do this. There's a way to learn the reward function. Here are some preliminary experiments on this particular problem that we played with. This is work that Jessica and Paul Monero worked on. The idea here is that we're going to learn a reward function with the property that if we optimize a policy against that reward function, it's as different as possible from a uniform random policies valuation according to that reward function. So it's a little bit tricky. The intuition here is that rewards are rare, and so if you act randomly, then you do not encounter a reward very often. And that means that if you try to find a function which gives you a reward rarely when you act randomly, and has the property that there's a policy that optimizes so that you achieve the reward often, you may find the right reward function. Okay, so this is relatively anecdotal here. We don't have any confidence yet that this is actually the right choice for how clicks, likes, dislikes, and doing nothing should relate to each other. But it turns out that you can apply this in a very systematic fashion, and it works. So we tried this on OpenML with 396 datasets, each of them having 3 or more actions. Right? And then there's sort of 3 different reward functions we can feed into our learning algorithm. One of them is a perfect reward function, which says, oh, you have a reward of 1 if you predict the correct class, and you have a reward of -1 if you predict the wrong class. Now, across these 396 data sets, the average performance was about 0.47, 0.48, something like that. So that's quite good compared to the next reward function. For that reward function, the performance was, the way that reward function was defined was, you say, if you choose the right action, you get a reward of -1. And if you choose the wrong action, you get a reward of 1. So this is a terrible reward function. It's one which shifts you to avoid predicting the right action. Because there's some exploration going on, you actually do choose the correct class sometimes, but you get a terrible performance overall. And the last one is a learned reward function. So you feed in either the bad or the perfect reward function, it doesn't matter which, as long as you do it consistently over the examples from a particular problem. And then you just learn whether or not you should think of this as the reward function or essentially a cost function, the negation of a reward function. It turns out that you can do that very rapidly, you can do it very reliably, and you can achieve an average reward which is very close to the perfect reward, even though the feedback being given to the algorithm is something which is very contradictory to the notion of a reward in many cases. Okay, so just to be clear, we're evaluating all of these against the ground truth, which is what is the correct action. And we're effectively learning a reward function reliably. Okay, so this is based upon a paper that we had at ICML, but this area I think is something there we're still figuring out what's possible. So there's a lot of potential applications around interpreting people, which could make an enormous difference in how well systems work. So a simple one is just speech recognition. Sometimes people say things in a little bit different way. The speech recognizer is good in general at picking up what speech is, but if it personalized automatically to individual people, maybe it would end up working better. And maybe you could learn to personalize based upon what's observed after you interpret something. You could think about eye-based mousing, right? So if where the gaze of a person goes, if you can learn to interpret based upon gaze, or to interpret what is meant by individual gazes, then maybe you can create new modalities for interacting with a computer. If you have a prosthetic, maybe that prosthetic could learn to automatically adapt to an individual person's gait, and maybe it could even adapt to changes in the gait based upon whether or not somebody is tired, or maybe the prosthetic gets damaged over time. All of these things become possible when you can take a feedback of some sort of reaction and based upon that reaction start to learn what is a good reward function. Maybe you can do gesture recognition. Maybe you can discover better and better how gesture recognition should be interpreted, gestures should be interpreted, so that you can get better and better performance, a more natural and kind of seamless interaction between people and computers. Or maybe you can even learn to interpret signals from the brain. This is a EEG here. There's no fundamental reason why we couldn't start to discover how what people are thinking about and how to interpret that and how to use that in order to assist them in doing various things. Or rather, I should say, we don't know a fundamental reason why that's not possible. So previously, I used to think about reinforcement learning as something where you had to have a reward function, the reward function was handed down to you. But now I've come to think of interactions as just naturally having reactions where you can start to discover what the reward function is based upon the structure of these reactions. We don't know the limits of what's possible here. That's something until to be determined, but I think in the next decade we will. And as computing becomes more and more personal, there will be more and more learning from these interactions, learning of the reward functions, more natural, more basic optimization based upon the reactions and not merely a predefined reward, which may be very difficult. It's hard to interpret exactly what a vector of sensory information from a prosthetic implies about reward, for example. So the key question here is how. How can we succeed here? There's quite a bit more work to do in terms of discovering what's possible and how it's possible. But it is clear that something is possible. We have existence proofs that we can learn reward functions. How large of a possibilities does this create? How many of these applications can we actually address in the next decade? I'm not sure about yet, but I'm excited about it. I think that we can imagine computers and people interacting in a much more natural fashion than they have been able to so far. In the future, I guess I expect that the computers will learn to interpret people rather than the tradition where people are constantly learning how to interpret the computers, and that will make a big difference. So this was a couple predictions for me for the next decade. I guess I would like to encourage you to think of this as a participatory sport. When you try to make predictions about the future, you're forced to try to cut through the details to what's really important. And I would love to hear about your predictions for the future as well. We have quite a few opportunities, I think, in reinforcement learning over the coming decade to change the way the world works. And the more the merrier is my general impression here. Thank you, everyone.